Bismillahirrahmanirrahim. Assalamu alaikum. Hope you are fine. So today is the first lecture of third week. We are going to continue with the ternary liquid extraction system equilibrium, and we will use it for calculating number of stages in this week. So before this, in first week we just got introduced with the liquid extraction system. Then in the second week we have studied something related to equilibrium, the same topic, ternary liquid extraction system equilibrium we studied, and actually there we discussed two type of systems, and for one type of system we introduced, or we just looked for an equation to calculate extraction, and when you are going to design a system, and for second systems we just were introduced to some diagram, ternary diagram or triangular diagrams, and we used those diagrams for some calculations. So actually this is in continuation of the last part of last week lecture, that was about this ternary liquid extraction system equilibrium. Actually we have to continue with the same system. So let's start this lecture. Here today I am going to briefly or quickly review some parts of the last lecture. Actually there were few problems to some students, so I think maybe others are facing same issues, so we will quickly go through those part, and then actually we have to extend few of those points. So this is from the last lecture. Then we will jump towards study of inverse lever rule and its utilization for finding extract and raffinate. So I will again go back to one example which we discussed last week. So I will introduce you that how you can calculate actually amount of raffinate and extract by using this something called inverse lever rule, and then we have to look for the system that we are going to design, or for which you can say that we calculate the number of stages in liquid extraction equipment. So we will briefly study how the system look, from where feed is coming, from where solvent is going, and then this is one Hunter-Nash method which we have to use for finding the number of stages in liquid extraction equipments. So we have to just briefly look at this method, and then we'll continue with this from next lecture. Okay, from last lecture there was something related to tie lines. Here you can see this, we have already seen. Due to this I have mentioned this slide is exactly from the last lecture. So this was data which was provided to us for drawing tie lines while we were discussing the topic of ternary diagram or triangular diagram. So here this is the diagram, and in this diagram you can see these dotted lines here. So these dotted lines are actually these dotted lines show tie lines actually. So tie lines are available in this system, and they are just drawn with the help of this data. Okay, just look, because you were facing some issues related to this. Here just see, you are given some data that glycol in water weight percent and glycol in furfural weight percent. Actually before that there was some data, and with the help of that data we used to draw this line which is called miscibility curve, or you can say binodal curve. So this line and it will end here. It starts from here, it will just move through this main area. This is plate point on this, and then you keep on moving and so on, you will reach here. This is drawn with the help of equilibrium data. And by the way, this same data, tie line data, is also provided through the equilibrium, but this is given here separately. While you jump towards the unsolved problem, there is the one table in which both data are actually combined. So okay, let's look here that with the help of first given equilibrium data, where there were three columns, one was furfural, then there was glycol and water, and you have just located the various points of this curve and then have drawn this miscibility curve. After drawing this miscibility curve, now you have to then draw here tie lines. So in order to draw tie lines, just look here, you are provided with some data points. So how you have to use or where they are located actually. Here I want to show you like this. You have one, let's start from here, 7.3 and 2.5. 7.3 glycol in water layer, percentage of glycol in water layer, and this glycol in furfural layer. So I told you that furfural was a solvent and the solvent rich layer is called extract, while the layer which is rich in the carrier is called raffinate. So here water side is this one, and due to this we have mentioned, we have discussed this, that this side is usually called raffinate. From which point this side, this plate point is the separating point. If you look on the right side of this, we have raffinate here, and if you look on the left side, we have extract. Actually if you just switch the main location of water and furfural, then this will just shift. It is not necessary always to be located on the left and right of plate point. Here based on this diagram, we have actually furfural on the left side of this diagram and water on the right side. So due to this, water rich phase is existing here on the right side and raffinate is here, while you can see extract written here, it is on left side because here furfural is in higher amount. For furfural rich side will be located on this side. So I was saying like here you have now water 7.3% glycol on water side, while it is on 2.5 on furfural side. Now I have to locate or I have to draw a tie line. So how can I draw? Just look, this is water rich side, you can see on water rich side. Otherwise if you just look at even only the values of this glycol percentage, you can easily locate that where it will be located. Like 7.3, suppose I have to locate 7.3. so you see these horizontal line are showing glycol. This is 100%, then 90%, 80% and so on, and this bottom line is actually 0% glycol, and this line is 10% glycol. So overall 7.3 is will be located somehow below this line, and 2.5 will be located on lower side even. So tie line actually connect the raffinate side with the extract side at equilibrium. So just you can see here, if I locate some point for 2.5 glycol, this is somehow 10, and you can see somehow definitely it will be like 2.5 here. So this point is located here, and on the other end water rich side you can locate 7.3. So 7.3 is also somehow here below 10. So you have to just connect now these 2 points with the help of dotted line, and this line is drawn for this point, first one 7.3 and 2.5. Now look at the second, that is 15 in the water side. So that's 10% glycol, and this is now 20% glycol. For this here, this is the scale for glycol we have discussed last time. So overall 15 definitely will be located in between these two, and this is the point where is my 15%. And now let's look on the other side of furfural, that's 5.2%. so here it is located 5.2%. Now what you have to do is just to join these two 15 with the 5.2, and the second dotted line is like generated, and so on. You will keep doing this. Let's look at some other value in between, like this is 47.5% and 15% in furfural side. So water side 47.5. Just look, this is glycol 50% line, and if you look at this here, somehow this is 50% line of glycol. And what is value here on water side, because definitely raffinate side we are here, and that is 47.5. so just below this here it is 40, it is 50, so this point will be 47.5. and now you have to connect it with the 15% on the other side. So we will move downward here, this is 10 and NAS is 15%. So sorry, 20%. So in between this, I think here in between these two lines, this is 15%. So if I just join this point with the other point, we will get this line 47.5 and 15, and so on. You will keep on moving, you will keep on drawing all lines here. Actually all are not presented. I think this point is just skipped from here because it will be too close to this main miscibility curve, so he has just skipped here. And the last point here is 41.5 and 41.5, and this is actually the plate point at which this is the one point in which glycol is same in both phases. And actually after this, due to this, we are jumping towards one phase region. Above this miscibility curve there is one phase region. So this is how you have to draw the tie lines actually. So tie line, so here each pair actually represent composition of equilibrium phases between two sides or two phases, extract and raffinate. So hope now this is clear to all of you, but still if you have any question you can ask me, you can send email. Now here one thing more which was causing trouble to some of the students, like here the slope of these tie lines. Slope of these tie lines can be like this, which you can see from this solvent towards carrier is upward, or sometime it can be like reverse of this. So let's look at this. Here actually tie lines can have different slopes. Some systems, such as there is an example of isopropanol, water and benzene, so exhibit a phenomenon called solutropy. What is this solutropy? Solutropy is actually the phenomena in which tie lines have different slopes throughout the system. Like here overall you can see that the tie lines have more or less same kind of slope, but overall you can see here this slope is decreasing, and overall this is becoming like somehow more or less close to the horizontal. If we have another tie point, another point, definitely it will be very close to the horizontal line. Here in such systems actually some slopes or some lines have slope in one direction, like it will be suppose upward direction, and then it will start decreasing like we have seen in our system. Somehow it will finally reach to the like horizontal line, and then below horizontal line some lines will have slope, tie lines will have slope like this one. So overall here you can see that this will be lying under dome, like in our system we have seen. So here slope is changing throughout the main system. When you are looking at this at various equilibrium points, slopes are different actually. For such system, these system which have solutropy behavior, so for such system moving from the plate point to the two phase region, usually plate point will be located here somewhere upward. So if you just move down from this, like you are entering to the two phase region, because you know plate point is the point which separate one phase from the two phase system. So when you move from plate point to the two phase region of the diagram, the tie line first slope in one direction, like I have shown you, like here they are upward from, suppose we just consider that this side here of the point of the triangle located on this side is suppose solvent and the other side is suppose carrier. So they are actually upward from solvent towards your carrier, as you have seen here in this example on the last slide. Then slope diminishes until an intermediate tie line become horizontal. So here you can see that it will keep on decreasing, and finally you reach to the something horizontal line with no slope, and then it keep changing, and now it will move in the opposite direction. First they were in the upward direction here with respect to from carrier to the solvent, and now they are moving like in this direction. So after this horizontal line, below this horizontal line the remaining line slope in other direction. So sometimes this solitary phenomenon disappears if mole fraction coordinates are used instead of like mass fraction. You know, remember that we were dealing with these liquids, and we said that we will write everything in the form of or plot on the diagram with the help of like mass fraction, but if you use mole fraction this can be avoided somehow. But now actually why I am discussing here, the point is on next slide. If you remember, when we have discussed this diagram, this example, and in this example, what was your purpose? Actually I will just bring you why I have discussed these various points and where you have to use actually, or where you are confused. Due to this I am just bringing again here the same example which we discussed. I will quickly go through this and I want to show you 1 or 2 points actually, how you have to solve this example. So in this example, for a quick review, maybe some of you didn't go through this or didn't remember. So determine equilibrium composition and amounts of extract and raffinate when a feed F of 100 gram of 45 weight percent ethylene glycol and 55 weight percent of water is contacted with 200 gram of the solvent or pure furfural at 25 degrees C and 101 kilopascal using data in figure 4.13. Actually we were in the section 4.4 at that time, and there it was the figure 4.13 and example was 4.7 from your book of 4th edition. So here actually you are contacting the feed which is actually only 100 gram, and out of that 100 gram 45% is ethylene glycol and the 55% is water. Now you have to contact it with the solvent actually for extraction of this glycol from this feed, and that solvent is furfural and that is pure, that means that is 100%. So now you have to use it, and you were supposed to calculate actually equilibrium composition and amounts of extract and raffinate amounts, that how much extract and raffinate will be collected and what will be the equilibrium composition, what will be the composition of this raffinate and extract at the end of the day. So this we were supposed to calculate. I have gone through this example in detail. So here is the solution which we have discussed in last lecture. So complete solution was discussed with you. If still anyone has any question, can post it by email, can ask it. So here I want to read to this point. So quickly, I told you here that what is given, data which was provided to us, then what was asked, I have discussed this. Then there was solution, how you have to proceed for this. So first of all we found how much will be the amount of mixture. Actually mixture is found from feed and the solvent. Then we calculated actually the composition of mixture, because this mixture is formed from feed plus solvent, and we know their amount as well as we know their composition. So we can use somehow material balance and can calculate. This is you can say overall material balance is applied here, that you are getting the mixture from feed and the solvent, and then you can use somehow component balance and can calculate the composition of mixture, which we have done already. So after doing this, what we did actually, we located some points on our diagram which was ternary diagram or triangular diagram, in which we located the feed as well as solvent and the mixture points. So then after locating them, I will just show you how we located, and then after locating them actually we have drawn a line, tie line somehow you can say, from point M and towards binodal curve to locate termination points of extract and raffinate, and actually they are used finally towards calculation of composition. So this is from the last lecture what you did, but now let me go back to that diagram. Here you can see this was our originally without this blue line, the diagram was 4.13 that he has referred, that was ternary diagram based on the system which we have discussed just before this example in the discussion. So overall you can see here we have located various points on this diagram, and I told you that solvent is 100%, as he said, pure furfural. So here you can see its fraction was given as 1. So overall you can see where is furfural 100%. This was the corner for or apex for furfural, that is 100%. So this point will be S point. Now come towards feed. You remember that feed was 55% water and 45% ethylene glycol, and here you can see that for ethylene glycol these are the horizontal line, this is 50% and other is 40%. So in between them here is the point that is actually 45% ethylene glycol, and then we look for this, that this is actually the edge or side of the triangle, which is which represents the mixture of ethylene glycol and water. So here when you have 45% ethylene glycol, definitely at this point water will be 55%, but still you can verify here water is 100% at this corner, then 90%, 80%, 70, 60, and this is definitely 55% for the water and 45% for ethylene glycol. So this was feed, and then we located actually the mixture here by using the composition of mixture, which we have already calculated, and actually we have drawn a line, straight line from feed towards solvent actually, and this mixture is formed from feed and solvent. So this mixture M point will be located on this main feed and solvent line. So after this, our next task was to draw the line for this to draw the line from M. I will just come back to that slide. Now our task was not just to draw this line, actually our task is in next step, and that is here you can see, first of all we located the feed, solvent and mixture point on the diagram, then from the mixture point M, draw a tie line towards binodal curve to locate termination points E and R. Actually we have discussed already in the lecture before this that here you have to draw a line to calculate raffinate and extract, and you know this is the water side, which is our carrier or the solvent available in the feed. So from plate point towards right side here we have this raffinate side, and other side here is extract side, which is actually rich in furfural. So here we have to calculate, due to this we are looking for E and R on this diagram. So now you have to draw a tie line from this point, passing through this point to find E and R. So how it should be drawn? You can see before this I discussed in the lecture that somehow our M point was located on one of the tie line, so there was no issue. You can just trace out that where this tie line is ending on raffinate side and where it is ending on extract side, so I can easily find the composition. But now you can see here M is located in between, this is not located on any tie line. So overall you can see this M is located in between two tie line, one tie line is above this here and the other tie line is here below this. Overall it is like straight line. I have just indicated here this one, and the other one is this. I have also posted one voice note in WhatsApp group that how you have to draw the tie line for this M point. Now just look. Actually this is called now interpolation of the tie line, because there are two lines above and below this point are given, and we have to draw one line in such a way that it pass through this M and then it reach towards other end. Overall you can see that I can draw here as in the next slide there it is given that the one line is given. Overall you have to look for the position of M, that where it is located, because now here you can see one thing, that slope of two tie lines is not same. If it was same we can just directly draw easily the tie line between them, but here now definitely location of M point will decide that what will be more or less the slope of tie line which I am going to draw here. You can see that tie M point here is more located, or it is like more close towards downward line. So somehow your slope will be between these two tie line, upward and downward tie line, but this will be like more close towards downward, because this point M is more close to this. So here when you draw straight tie line, somehow it will reach here, and you will also connect this on the other end. So overall if you see here when you draw this line, somehow your point M is as located more close to the downward tie line, so here it will be more close to this point of lower tie line. So this is how you have to draw. Actually I have shown you here in next slide few more example for drawing the tie line, So let's look at those. Just look at this diagram. Suppose this was already discussed M point in the diagram. In the lecture it was discussed that your point, mixture point, was located on tie line, so there was no issue. Now just look at this. Here I have just brought new M point. This is the mixture point which we have got after calculating composition from feed and solvent, as you have done in last slide. So when you have located this M point, now you have to look for raffinate and extract. So just draw the tie line here. You can see here this tie line. Overall you can say that from here I can draw many tie lines. Definitely you can draw, but you have to draw this tie line between these two lines. Overall between these two lines, now look here, this is somehow, this M point is located in between these two tie line at this point, where it is located. Overall just look between these two tie line, this is somehow in between. So now when I am going to draw the tie line, that should be located in between these two tie lines, but overall you can see that this has higher slope as compared to this. So when you draw in between these two, definitely it will have slope in between these two lines. Now look at another point. In this diagram you see this is the original M point, and now I have shown two more points for M. One point is this and the other point is this. So let's look at the tie line for these. You can see here, from the discussion which we have done so far, overall this point M is now located, or it more close to the upper tie line in this region. So overall the tie line which will be connecting, or which will be passing through this M point and will be joining raffinate and extract composition, that will be more close, or which will have behavior which is more close towards this tie line as compared to the down one. You can see here. And then now this other point is which is more close towards lower tie line. So overall when you draw the tie line here, you can see this, here we go, the green one. So overall this has slope which is more close towards downward tie line. But overall if you look either at this red or even green tie line, they will have definitely slope in between the upper and down tie lines which are already given in the system. So this is how you have to draw. Hopefully now this is clear after these examples. So suppose your M point is located anywhere inside the system, so just draw a line. Overall you can see just here that on this end, extract end, because we are very close to here, between these two tie lines, they are already very close to each other. The lines between which we are just locating our next point. So you can see there will be very small difference in the composition, but on raffinate side definitely there is a difference. You see here that by changing the position of this point, mixture point, like raffinate composition is changing from here this to this, there will be a difference in the composition actually. So due to this it is important to draw the line carefully so that you get close to the exact composition which you were looking for. Here, so this was from last time, when M was located, so you have drawn a line which have actually the slope between two points which were given, like here you can see in this diagram easily that this was our M point which was located on feed and solvent line, and then we have drawn here the tie line. And what you can see here, you can observe one thing, like this M point was more close towards like downside tie line. So overall you can see that this will have slope which is more close towards this, like we didn't draw something like from here and moving towards upper one. Overall this is more close towards this lower tie line. So you have to adopt this procedure, you have to use this procedure, and hope so you will get accurate results. Next point here, one thing I asked you to last time ignore these numbers, but now we have to use these because mean 1-2 students have asked this, and maybe later you can use this point. Actually I don't want to indulge you in this measurement. Actually, by using ruler, I asked you to go for some calculation and directly use material balance, but we can also use, as he has provided here, with the help of ruler you can measure the lengths and they can be used for calculation of something. So let's look at that. Before I jump toward that point, I will show you again the solution and there where it can be involved, this point overall. You can see up to here we have discussed that extract and raffinate composition, how you have to read. So here now you have to look at this, like for finding the amount E and R. So what we did for finding the amount of extract and raffinate, we have applied component balance, and you already know here we have applied these two component balance for component A and component C, and by solving these two. Here I have told you to calculate extract and raffinate by using component balance, but we can use that inverse lever rule for calculate. Use another method that's called inverse lever rule method to calculate E and R. Actually this was discussed in the example somehow, but I have just skipped, but 1 or 2 students have asked, so I'm just going through this quickly. So you can also use that method. Actually come here, and that's actually inverse lever rule, but before inverse lever arm rule I just want to show you the lever arm rule. Somehow maybe you have studied this during FSC. Here you can see that you have some system. There is fulcrum and beam, and 2 weights are placed on this, and overall you can see that, suppose we name it like M1. Here this is M1, one mass, and other is M2, and here this system is balanced because these are the same mass. You can see they are 100 pounds and they are placed actually at the same distance from this center. So if you just change their distance, definitely this balance will be disturbed. So like if sometime you have to find some values of something here, suppose I say okay, from this center, before I go for that formula, from this center towards this M1 my distance is suppose x1, and if I just look at from this center to on the other side, so it will be up to here and it will be like x2. Suppose I have to find these distance, or sometimes these mass were given. So what we used to use is M1 over M2. The ratio of these two masses is equal to x1 over x2. What was here? Suppose now you know both of these masses, so these like suppose 100 over 100, so their ratio is 1. Overall the ratio of these distance should be same. That what was it, like 10 over 10, it will be like 1. The units are in inches. Suppose now I just change one of these mass and I want to check that what will be the effect of these distances. So overall suppose you just bring here 200 pound. Suppose you bring here 200 pound on this side, so what will happen towards 200 pound? Now definitely the balance is shifted. Overall this side will move downward, definitely because mass is higher on. To use this system, and actually we want to locate now, or we want to calculate that at which distance this M1 should be placed to keep the system in balance. So it will be like 200 over 100 like on the other side, and now what you are looking for, you are going to calculate this x1, and definitely here you have already x2, so that's 10. Now just solve this, and what you will get, x is equal to x1 is equal to 20. So it's if you just place this mass x1 of 200 pound, so you have to place it at 20 inch away from this center so that they can stay in equilibrium. So overall this is how it works, or this is called lever arm rule, in which you just take the ratio of the mass, and that's some have same ratio as their distance from this center point. But if suppose I say I have to inverse it, so how it will be inverse? Just mean this is simply in this system lever arm rule is used, but if I have to inverse it, so inverse is just if I have m1 over m2, so its inverse will be like equal to x2 over x1. Though this is not correct for this system, but I'm just giving you the example here. Mean like your inverse rule system is if you are looking for one quantity, so the quantity related to this, like there was x1 distance that was from this fulcrum towards mean this mass m1 that we have named as x1, that is now inverse located on the inverse side of this mass, that's not directly or on direct side, like you have seen here m1 x1, this here from here you can see they have direct relation, but here they have inverse relation. So suppose if you are looking for some rule or some quantity in which you just locate some point inverse to its one side, like here mass 1, and if its distance is inverse to this, so this will be in the denominator side. So here we have to use some of the same inverse rule, and one thing, if still is not clear, kindly just Google it. Okay, right, here this rule now, inverse arm rule, is used in our calculation, so that's widely used in calculation. This lever arm rule and inverse lever arm rules are used here for calculation in diagrams of ternary system and other. So to determine the amount of E and R, inverse lever rule can be used. Before we look at this, just go back to that diagram. Here you can see, now we have to use some distances and we have to calculate E and R. So overall you can see this M is located in between E and R, and overall this M is at the distance of EM from this E to M, distance is EM, and that will be actually here it is 0, so overall this is 1.97, this distance from here EM, and other is R from here M to R, so it is MR, and that will be actually just 7 minus this 1.917, so overall you can see this is located here. So now I am looking for actually E and R, and they can be calculated from here if I know these distance, as well as if I know some of these values of either E or M or R. So overall you know that when you started this problem you already are aware about the value of M. M was actually the sum of F plus S, and that is feed plus solvent, and later this M is actually splitted into this mixture is split into extract and raffinate, so that E plus R will be actually equal to M. So we have to use this stuff now for finding E and R. Suppose I want to find the value of E and I will relate it with M, E over M, that will be equal to, for this formula is actually E over M is equal to actually MR over ER. E over M is equal to MR over ER. ER is the distance from E to R for M, and for E we are using MR. Actually for E is located on the left side, and you have to use the distance from M towards right side. So this is the inverse, like you are not using the same side, you are inversing the side distance. For E you will be using here MR. So E over M is equal to MR over ER. Now we know three of these quantities, and the fourth one, E, can be calculated. E is the extract which you are looking for, M is the amount of the mixture you already know, MR is the distance you have seen in the diagram, and ER overall you have seen. So these distances are provided here, that E you are looking for, M was 300, and MR, as I have shown you, R is located on the right side, and from M towards that right side there were two digits given, 7 and 1.917. You can go back to that diagram and you can look that MR is actually this distance, I have already told you there, and divided by ER, overall distance from E to R, and that was 7. So if you solve this you will get E as 218 gram. So Now when you have calculated E, as I told you that mixture is obtained separated into the extract plus raffinate, so you can calculate from here the raffinate is 82 gram. We can also use the R, or we can also calculate R instead of E by using this inverse lever-arm rule. So overall, just look at this here. For R, if I am looking for R, it will be R over M, and for R over M it is like, now for R is located on the right side. Now what we will have to do, we have to take the distance of the left side, and that is actually ME. For calculating R, we are inversing it. We are not using the distance of same side for R, we are inversing it. Due to this, they call it like inverse lever-arm rule, and that M is correlated to ER shows the overall distance, and M is mean the mixture complete amount that was coming from feed and solvent. So this ER, due to this, we are using as a whole for M. So you have to just put the values here again. R you are looking for, M is 300, and ME, that was 1.917, because your ruler has 1 and 0, so this will be 1.917 minus 0, so overall it is written 1.917 and divided by 7, that is ER total distance, and overall R you can see here it is 82 gram. And same, if you will apply the balance like M is equal to E plus R, you will get E is 218 gram. So overall you can see that these values are more or less close to the values you have calculated through the material balance, that was 220 and I think 80. So this inverse lever arm rule also provide you these values, and you can use this system if you are interested for this. But you have to do, you have to look for something ruler, you have to measure the values, and you can use those in these calculation. So that's it about inverse lever arm rule. Now we have to jump towards something else, and that is miscible and immiscible solvent system ternary diagram. If you remember from the last week, I think that was lecture 1 of last week, or you can say overall lecture 4 here. So in that lecture we have discussed equilibrium, and before starting that equilibrium we said that when we bring the feed and solvent in contact with each other, there will be various main possibilities, and out of those possibilities we picked 2, and that was miscible solvent and immiscible solvents. So overall for these miscible and immiscible solvents, then we started with some calculation, and you have seen for miscible systems you have drawn one, you have derived one equation, and then for immiscible system we started with these ternary diagram. So overall you have seen this kind of ternary diagram, and this is for which kind of system? Definitely immiscible system, because we started with the immiscible, not immiscible, that was partially miscible solvent. Actually, first of all, in that lecture you studied immiscible system, and for immiscible system we have derived an equation, and then we jump towards partially miscible solvent system, and this is the diagram for partially miscible system, which we have seen in whole discussion before this and in the last lecture, that somehow your extract will contain some amount of water, while your raffinate contains some amount of furfural. That was actually the solvent. But for, if you look for the diagram, these diagram for immiscible system, so they just look like this. As you have seen here, this diagram is for immiscible solvent system. So in your book, actually he referred to these system which are partially miscible as system 1 or type 1, and these as type 2. He have just given these type 1 and type 2 names, so when you are going through the text, so don't get confused. Type 1 are for these partially miscible system, and type 2 diagrams are for immiscible system. So if you have to just somehow distinguish between miscible and immiscible system based on the diagram. So from here you can get the idea that there will be a complete dome, and overall there will be this binodal curve for these system which are partially miscible. But for immiscible system you can see that that's not the complete one. Here you can see raffinate phase side and the other one is extract, and that's not the complete diagram for these system, immiscible system. So based on diagram you can just identify those system. Now after this, actually up to here, if I just summarize, we have discussed the ternary diagram. Now you can easily read these ternary diagram that where and which component is located, how its composition I have to find, where there is a binary mixture, where there is a complete ternary mixture like one phase, two phase, where is plate point, what is binodal curve, and on which side of plate point there will be raffinate phase and on which side there will be extract phase. By the way, up to here all the diagram which we discussed, when raffinate was located on the right side of the plate point, but here in this diagram it's good to see that like it is located on left side while extract is located on right side. So how this happened? This is, as I told you, this is been based on location of your solvents. Suppose if you remember that furfural was solvent in our system and that was located on the I can say left apex, or this point on this side, that was furfural, and here at this location where now it is solvent, as here was water was actually carrier in the feed. So now when you brought this carrier to the opposite end, so definitely its line will vary, it will be here 100%, and then they keep on decreasing, and overall on this side here they will be like 0. And for this solvent, now definitely you can see here it is 100%, so there will be some lines for this, and at the end here it is 0. So there is no issue either on which side, you just keep this carrier and the solvent. And it's better to place solute on the top here, because with the help of this you can easily get this diagram which is easy to read. If you just place solute from somewhere here downward, so your actually curve will just shift like this somehow. If you will get curve like this, then it will be difficult to read through the tie lines, and you have to just turn the page. So it's better to just put solute on the top. You will see in the most of the diagram provided in the book and the other sources, they have just solute on the top and the both solvent on the bottom side. So it is there is no problem either you place on which side, so there is no issue. Just it will shift your raffinate and extract region. Just remember this, because if you have in your mind that only the left side is extract side and the right side is raffinate, then there will be problem. So it's better to just label them when you know that this is carrier, and the carrier rich side is the raffinate stream and the solvent rich stream is the extract side. So just label them on your diagram so you don't make any mistake. Now when you are done with this system, actually we have to use these diagrams for the calculation of number of stages. So here this method which we are going to use is Hunter-Nash graphical equilibrium stage method. In this method we will study here stage wise extraction calculation for type 1 ternary system. Type 1, now I have told you already that type 1 are those system in which your book actually refer type 1 towards partially miscible solvent system. So they are usually we have, as we said, that these are the common system which we come across in industrial application. So we have to design our system based on these system type 1 ternary system. For this Hunter-Nash method is discussed, and let's look at the system and its specification for this method in this lecture, and then from next lecture we have to move towards next stages. Overall we will look at the schematic diagram for a counter current continuous flow and an equilibrium stage extraction cascade operating isothermally at steady state. What does all this mean? Actually, we are going to discuss first of all counter current. From the first lecture, you remember we said that counter current is the best, and counter current gives you the better results. So due to this, we are going to consider here the counter current system, and this is continuous flow, some solvent and the feed are continuously entering to the system and leaving, and there are an equilibrium stages. Number of equilibrium stages are there, and this is cascade, that is continuous system. Actually, if your extract and raffinate are moving from one phase to the other phase. So look at this diagram. Cascade is continuous, like your feed enter from here and it is jumping from getting getting purified, and it is moving from stage 1 to stage 2 and so on towards end, and the solvent is entering from the end phase and it is moving continuously. So that's the cascade system, to jumping of liquid from one phase to the one stage to the other stage, continuous manner. And this is isothermal system. It is at same temperature. Actually, I have told you that this temperature pressure are effective, but out of those temperature pressure, in the last lecture we discussed that these equilibrium data is affected, but usually pressure does not affect too much, but temperature definitely affect, and this equilibrium data is changed. Due to this, your diagrams will change and your results will change. So you have to take care of this, that your system here we are considering is isothermally operated. So in this system, each stage include, here you can see these are the stages. Actually, stage 1, stage 2 and so on. There will be in between, there is small n stage and then n stage and capital. This somehow you have seen the system which we discussed for absorption. So what we have to do, or what we used to do, there was a similar, like we have one column in which we said that this is stage 1 and so on, and then you used to jump towards end stage. So this is also described in the similar manner. So each stage here actually includes mixing and phase separation. Overall, he has shown that this in each stage actually you will have mixing as well as separation, because you can get confused, okay, it is only mixing and no separation is taking place. So at each stage actually mixing as well as mixing between like feed and the solvent, and some extraction occurs and then they are separated. So each stage indicate this system. Then stage numbering, you can see here, because number we have to later use for derivations, we have to use somewhere. So numbers, they are numbered from feed at number 1, feed from where the feed is entering is stage, as that stage is numbered 1, and then next is number 2 and so on, and the end stage is from where raffinate is leaving. And he said that stage number begin at the feed and opposite to the end at which solvent enter, because this is counter current system, so definitely they will be entering from the opposite side. So the side from where feed is entering is given as number as stage 1. Maybe even you can reverse it, no problem, but here when we are going for derivation and to be consistent with the book, we are going to use this same convention. So overall you can see that feed is entering to this stage 1, and the raffinate which is leaving from this stage is given name as raffinate R1. So when there is R1, it's mean raffinate coming from stage 1, and E1 extract coming out of this stage 1, and something extract which is entering extract, actually he is calling it extract. Here you maybe you will considering definitely this should be somehow solvent. So extract is actually solvent rich phase, so that is coming from stage 2 and now it is entering to this stage. So due to this it is named as E2 and so on. You can see all other numbers. So here this E1 is final extract feed rate. Final extract mean when you are done with all the extraction, and the final extract feed rate, that's named as E1, and this final raffinate feed rate is named as Rn. So overall when you look at this system, at each stage actually the equilibrium is established or assumed. First of all their mixing will take place, and then for separation definitely we need to go for equilibrium. So then equilibrium is assumed at each stage. When equilibrium will take place, definitely then you get separated actually at equilibrium the extract and the raffinate. So at any intermediate stage, the component in extract and raffinate, they are in equilibrium. I mean, for any stage, and shows any stage you look in between, the extract and raffinate living from that stage are actually in equilibrium. Suppose if I look at this first stage, so for first stage when they are living extract and raffinate, they will be in equilibrium with each other, mean they are separated. And then if you look at this E2 and R2, they are, and so on. For each stage, the raffinate and extract will be in equilibrium. And by the way, mass transfer of all species takes place at each stage. You remember that like here these are the partially miscible solvent system. So in this, only extraction of solute does not take place, solvent are also exchanged with each other. So this phenomena will be taking on each plate, like solvent transfer from feed towards solute transfer from feed towards the externally introduced solvent, as well as some of the solvent or carrier which is a part of feed is transferred towards solvent, and some of the solvent externally introduced, this solvent will become part of this raffinate feed side. So now when you know this system, we have to actually continue with this system, and we have to calculate the number of stages. So overall, when you look at these system, for using these ternary system to find the number of stages, we require 6 variable. Actually its degree of freedom is 6. Here we are not going in its detail, but overall in the book it is discussed. You can quickly go through that. And by the way, here again we are back in this from this section. Actually we just jump back towards chapter 8, from where we were already discussing liquid extraction system basics and then equipments, and then we jumped in between towards chapter 4, and again we are back here towards section 8. So you can go through, this is 8.3. Quickly go through that. Initially he has discussed some steps for the design, and then he has started with this calculation of number of stages. So just go through that. So overall here we are going to specify some variable, and in your book there are mentioned the various variable which you can fix, but the most common with which we usually use to move, or which you can easily locate and find and can design those system, are given here. First of all, you should know the feed flow rate and its composition, that which components are there, and what are their percentages, and what is overall feed flow rate, as well what is solvent flow rate and its composition. So if any of these information is not provided, first of all we have to figure out, or we have to find this information. And operating temperature, that's important, because you have to look for equilibrium data. So when operating temperature will be known, you can easily find it for the system, or you can as we discussed that the liquid extraction system data is usually experimental, and we get in the lab, so you can perform some preliminary experiment to find that data. And then here up to here, this is 1 point, second, third, 4 variable, 5 up to here, these are the 5 up to temperature. Now 6 one is either composition of the raffinate leaving the end stage, from the last stage when it is leaving the raffinate. So what is its composition? Either it should be known as a 6 variable, or the composition of extract leaving from the first stage, that was represented with E1. So either its composition should be known. Here x and y, these are actually the mass fraction, just to differentiate them. Both are mass fraction, they are not anything like mole fraction, because here we are dealing with the liquids, and we will talk only about the mass flow rate and mass fraction. So xi is mass fraction of any component of the feed, and yi is the mass fraction of any component which is the part of solvent stream. And you know that then solvent rich stream become extract. So due to this, here we have shown that this yii and xi, that's raffinate feed is carrier rich feed. Due to this, you are using the same convention xi or n, or xi any component x component I, its mass fraction in raffinate that is leaving from nth stage, and any component its mass fraction in extract which is leaving from stage 1. So when these 6 main parameters are known, then you can determine these number of stages required for some specific purity or this main extraction using triangular diagram. You can also use some other parameters which are given. Sometime you can skip this solvent flow rate. If I just skip solvent flow rate from here, so definitely I have to look for something else. So then maybe I have to specify both of these to fulfill the requirement of these 6 variables. Actually, when we design the system, you will look that if these at least 6 variable are not known, you can't go for number of stages. And by the way, this system or this method which is called Hunter-Nash method, that involves now next 3 steps, or you have to solve this problem in 3 steps from where we have to start our next lecture. So up to here you are introduced with this system, that how it will work, which variable you will need, and how the system or streams will be numbered based on multi-stage system. So that's it in this lecture. What we have discussed initially, we just started with the last lecture that was about tie lines. We discussed somehow how you have to draw the tie lines and how these tie lines are located inside the system, and if you have to draw some new tie line which pass through this your mixture point M based on your feed and solvent, so how you have to draw that tie line. Then we discuss inverse lever rule for calculation of extract and raffinate, and then there is after this we have started with the preliminary system introduction about number of stages, the method which we are going to use, and the system which we have to adopt for calculating this number of stages, that the ternary diagram, and in this we need some specific number of variable which we have discussed. So next lecture we have to continue from here. Thank you so much.